Okay, so we are ready for the final round of this stage. So the opponent challenged the reporter for the problem.
Problem number 3.
Okay, accept. So please go to write down your name on the backboard. reporter, so you can start your presentation.
Greetings. Today I'm going to report problem number 3, lato-lato. First of all, I would like to clarify the following statement. Attach a ball to each end of the string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the ball starts to glide and oscillate with increasing amplitude. Investigate this phenomenon. These are the main focuses that I want to underscore. First, the effect of the collision in this phenomenon and the relevance between the frequency of the pivot and the amplitude. Let's take a look at the observation video. Here we can see the oscillating pivot and the increasing amplitude. It is possible to regard the pivot as the origin of the reference frame. So we can see the equivalence of gravitational field. And after this, we can calculate the acceleration of the ball, and trivially, this is the angular acceleration of the ball. And these are the notation. Here we approximate the motion of the pivot as the sinusoidal wave. So here we get the equation of motion of the pivot and substitute it into the angular acceleration of the ball. We acquire this equation, and again, these are the notation. Nonetheless, the previous equation of motion I didn't consider about the damping. So this is the new one, fixed equation of motion, which considers damping, and this is modified to an ordinary differential equation. Here we can classify the movement into two phases. Phase 1 denotes the single collision phase. As the energy accumulated, the system reach its maximum amplitude, which will lead to phase 2, which has two collisions in a period. And there's no need for further discussion for phase 2, since the amplitude don't increases as the problem statement mentioned. Here is the numerical solution. We can see a nodule. Under resonance, the amplitude will reach maximum at 2 times natural frequency, and which I will prove it by experiment later. And here are the angular velocity versus time graph. We can see the accumulation of the energy will cause the larger angular velocity. Here is the phase space, which I will draw real one in a reality later. Here is the experiment 1. I would like to discuss about the equivalence of gravitational field. These are the equivalent. Here, since after a series of affable mathematical process, I should have the magnitude of G if my theory is correct. Here is the result I acquired. Here we can see the dense points here are very close to the magnitude of G. The loose points, however, are affected by the collision and damping, which I will discuss in the next experiment. So from this graph, we can get a nodule is that my theory is correct. And these are the equivalent of the second experiment. In this experiment, I would like to evaluate the coefficient of restitution and also consider about the damping. Here is the method. Attach the lato-lato on the support, provide the initial amplitude to the lato-lato. Afterwards, without offering further effect, measure the velocity and angular velocity. And the coefficient of restitution can be calculated via this equation. Here is the theoretical correlation between the damping ratio and the coefficient of restitution. And we can calculate it by this. We substitute the oscillation of the pivot as 0 into our equation of motion, and we can rewrite it as this. Here we can fit it in the damped sine wave. And the way I acquire the theoretical correlation is by this calculation. Here is the result. The slopes indicate the coefficient of restitution, and we can see all the slopes are lesser than 1, which indicates that they are all in elastic collision. And this is the result, the fitting result. We can calculate the damping ratio by the damping factor and the angular frequency in the damped sine wave. Here is the result I calculated. And in comparison to the one I evaluate with the theoretical correlation, we can see the damping in the reality is much larger than the one just considering the collision, which means other factors matters. Since evaluating other factors are demanding, it is more practical to do further research with this data. Here's the third experiment. In this experiment, I would like to measure the natural frequency, which plays a critical role in the resonance. So this is the equipment, and the method is quite simple because it is similar to simple pendulum, except the angle is very big. And though it should not be linear, but in the theory, because we cannot use the small angle approximate, but I still get a very clear correlation between it, and from this I can do further research with the natural frequency. This is experiment 4. In this experiment, I will talk about the resonance. Here is the equipment, and this is the result. I adjust the natural frequency via changing its length. So also we can see, since the unit of amplitude is rad, so the one with a longer length will have a lesser amplitude here. However, they have a common, is the one is more close to the natural frequency, 2 times natural frequency. The amplitude will reach the maximum, which I have shown in the numerical solution. And the last experiment, I would like to talk about chaos. So the methodology is to oscillate the pivot, measure the deviation angle with respect to y-axis and the angular velocity of balls. After extracting the phase portrait, we introduce time to analysis and evaluate the Lyapunov exponent, which plays a critical role to describe the chaotic motion. Here is the definition of the Lyapunov exponent. And in brief, it just find the 2 points that their initial conditions are very close to each other, and then calculate their distance, and using this function to see if they are far from each other or not. And the Lyapunov exponent will be this, which we will see it is the slope of the graph. But first, I would like to talk about the beat. Both in the experiment and the numerical solution, we can observe the beat. And there's a difference, is that the one in the reality has a larger amplitude. This is because the volume of the ball, which our theory didn't consider about. Here we do the Fourier transform. We can see a very close peak value, very close to each other, which cause the peak. Also, in the numerical solution, we can also observe this situation. And here is the phase diagram. We can see when the amplitude is increasing, it will drop back to the steady state of equilibrium. And this amplitude in this situation is not very large. We can see they are very close to each other. And in the theory, in the numerical solution, we cannot see the steady state of amplitude. This is because in the reality, the spring phase level will slack, and because the frequency deviation, the steady state will occur in the reality. And we can also observe that this is very close to 0. However, there is some blink between 2 balls' status. And this is because of the volume of the ball, which I have said that we didn't consider that in our theory. Okay, and in this page, I will talk about these 2 different graphs. We can also observe the beat. However, it is not as obvious, or I would say I cannot observe it very clearly here, because when the frequency is higher, the noise also increases. And we can see the angular velocity versus time is lower than the previous one, since it is far from the natural 2 times of natural frequency which I have measured. And we do a Fourier transform to see both in the experiment and the numerical solution, the noise increases when far from resonance. And here is the other phase portrait. Here we can also observe the steady state range of amplitude, but it is more larger. This is because it is less ordered and also in the numerical solution. And from this, we can't even see the steady state of amplitude. It is invisible, and neither in the numerical solution, which originally will not have the steady state. Okay, and this is the result that the Lipmann exponent we calculate. So from the previous theory, we can see the slope of the graph is the Lipmann exponent. And also from this, we can see the chaotic motion will not decay. So it is unceasing chaotic. This is the nodule of this experiment because it is quite a huge experiment. So B can be observed both in experiment and numerical solution. And as the frequency increases, the noise escalates, leads to obscure beats. And also, we calculate the Lipmann exponent to see if it is chaotic or not. So these are the conclusions. The first one, the oscillation of the pivot causes the variation of the equivalence of gravitational field. There are various factors lead to damping. Instead of utilizing the theoretical one, explaining the one we measure is more practical since we don't want to evaluate the diverse factors. And when the oscillation of the pivot has the frequency 2 times natural frequency, the amplitude reaches the maximum. And last but not least, lato-lato is a chaotic motion. Thank you.
Okay, so question from the opponent to the reporter.
Okay, so I have some question for the reporter. So first, for the experiment equipment, how do you make the pivot?
I use the Lego machine.
Okay. And can the boat go up and touch each other?
You mean phase 2?
Yes.
Oh, just as I mentioned, it is no need to discuss that since it doesn't increase the amplitude, which from the statement inquire us to do.
Okay. Then please turn to page 18. 18.
Okay, here.
So why does the omega is decreasing?
You mean the angular frequency?
The red.
The grass? The omega? Oh, I see. This is because the damping, which is critical in this experiment.
And please turn to page 26.
Okay.
How do you create a chaotic motion?
The lato-lato itself is a chaotic motion, especially for a higher frequency situation.
Okay. And page 33.
Sorry, we have some technical problem. I'm sorry, but you can still ask your question.
How do you explain the unclear result in the 33 graph?
Oh, you mean because the higher frequency increase the noise that cause the chaotic motion.
Okay, time's up. Preparation time for opponent. 3 minutes. The opponent take the floor.
Okay, so I am from Chinga Technology, and I'm going to talk about the lato-lato. So the problem statement: attach a ball to each end of the string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the balls start to collide and oscillate with increasing amplitude. Investigate the phenomenon. And the key points in this problem is collision and frequency. So the overview of the report. First, the beer part. They use the sign equation to explain the movement of the ball and separate the whole movement into two parts with phase 1 and phase 2. Next, the experiment part. Enough data to support the theory. And the conclusion. The lato-lato is a chaotic motion. Then the advantage for the reporter is many experiments can support the theory, and there are clear numerical models. And for the suggestion, to explain theory more and to show the experiment video. Thank you.
Continue.
So I'm gonna ask the experiment setup part.
Which experiment?
How
I have
do
5
you-
experiments.
Experiment setup.
I have 5 experiments, so which one?
Okay, so can you explain the equation in a more easy way?
You mean the equation of motion?
Yes.
Oh, okay. Okay, here, this is the equivalence of gravitational field. Can you understand this part? Yes, so using the formula of acceleration of the ball, so this part is applicable for you.
Yeah.
Okay, and so by dividing the length of it, we can acquire the angular acceleration. So this part,
So what is the angular acceleration?
the angular acceleration is like acceleration, but except it is like on the circle.
Okay.
So, and for the next part, we substitute the acceleration of the pivot into the equation of motion that I just mentioned in the previous page. Do you remember that? This one. Okay. So, the last one I didn't consider about the damping, maybe in my experiment 2 or 3, and so I modified the equation of motion into an ODE. So this is the equation of motion. So I think this is applicable for you, right?
Okay. Then the next question is about the experiment one.
Okay, so which part do you want to inquire into?
Because I'm not good at this in the English, so I cannot understand what you do in the experiment one. So maybe
Okay, so I remember you asked me before in the quick question, so I use the Lego machine to oscillate the pivot. And from my equivalence of gravitational field theory, if I times it with some like cosecant and add back the acceleration of the pivot, I should get the magnitude of g. So is this part applicable?
yeah.
Okay, so I think that's all for my experiment 1. So do you want to disclose more about the data?
So why did the data is more? There are more dots on. There are more dots that isn't on the 10. Okay.
Oh, the loose points are affected by the collision, or let's say other factors that cause damping. It will change its acceleration.
So why do you need to, in the experiment 5, I guess, why do you need to detect the frequency of the sound?
I have never detect the frequency of the sound.
Yeah.
I don't know what you mean.
You say that you have you say the sound of the frequency decrease.
No, I never talk about the sound of the frequency of the sound. I'm talking about the frequency of the motion or pivot.
So it's the motion part.
Yes, it is about the motion. I never discussed about the sound.
Okay, can I see that part?
You mean experiment 5?
Yes.
Here. So which part do you want to discuss about the methodology part or the sound?
So I think that you say lateral movement is chaos.
Yes.
Yeah. But I think that you can detect or you can say that the velocity of the ball when collide is like they can lose energy, right? Or they don't lose energy. So how do you think that this chaotic movement?
Oh, the chaotic motion can be verified through calculating the Lyapunov exponent. So when I'm reporting this part to understand this.
Yeah. Can you explain?
Okay, so in a brief ways to describe it is I pick a very close, the initial condition which are very close to each other, and then calculate their distance after times, and divide it by time. So I think I should give you, I think I should show you the graph to explain. So here, the slope is the Lyapunov exponent.
So the chaotic motion is like you detect two positions and
Actually, I use 6-dimension space to calculate this.
what is 6-dimensional space?
Oh, the 6-dimensional phase space includes the two information for two balls and the information of pivot, which I have manifest in this page here. There's a ball, there's a ball, and also some acceleration or maybe some angular velocity.
And so can you explain what is damping?
Okay, so the damping is a kind of energy loss. It's a method that we calculate the energy loss. So what do you want to ask?
Okay, about this graph.
Okay.
You move the Lego bricks up and
No. In this experiment, I didn't oscillate the pivot because I'm calculating the damping. So I can't give it external energy.
So you started and never changed to let the ball just.
Yes, I only provide an initial amplitude.
Oh, okay. And for page 34.
34. Here.
Why is the bottom part, right? This part is not the same.
Because the Lyapunov exponent is to describe the distance. So we cannot ensure that after every period the motion will be close to each other again. And if we let the time to go here further, we can see actually their bottom is rising.
So you said that you analyze the 6-dimensional things.
Yes.
So would you like to add like the acceleration into the dimensional space to analyze it more?
Actually, the sixth phase is the position of the ball and two balls, and also the velocity of them. And the velocity and the position of the ball, and also the position and the velocity of the pivot. So I haven't put acceleration into this for further inquiry.
Next question about experiment 3.
Right here. Natural frequency.
So can you explain how do you do the experiment?
Okay, I give a huge fixed angle and then just release it and using the tracker to record its like maybe frequency or period.
Okay, so can I see the graph?
Okay. Yes.
So why is the y is s squared?
Because then I can maybe discover a linear correlation. Because in the theorem, if we use the small angle approximate, we may get a linear correlation. Though this is not a small angle, but I still require this.
Can you explain it again? Why? So if you use the s on the y face, then how will the graph look like?
Can you please rephrase your question?
If you replace the square s squared to s, then what will the graph look like?
It may look like and maybe like equation of two just like this.
Oh, okay. And the question for experiment form.
Experiment. Okay, let me explain. The last one I'm talking about is quadratic equation. If you have heard of it. Yes,
Can you
quadratic.
explain?
It is the highest power of x is 2. Quadratic.
Okay. So this one do you add another energy in the movement?
The energy provided is unceasing because the Lego machine is constantly oscillating.
Okay. So this one, the Lego machine is giving the Laplace power.
Yes, the unceasing energy.
Okay. So it is the resonance of
The resonance is resonance is we can better account for resonance in this graph. This is about the resonance.
Okay. So you say that you can explain the lasso with the phase one. Then in the phase two, the lasso will bump on the upper part.
Yes.
So do you think that the upper part can affect the whole motion?
Yes, the upper part also have collision, and maybe we can calculate it with my damping experiment to explain it. However, I don't think we should discuss about phase two since the amplitude will not increase because it is the maximum.
But I think like lasso is a game about the ball and the string. So that if we play the lasso, we often just turn the phase one and to phase two. So
Yes, you can. That is just the maximum amplitude for it. So you can just try to estimate the natural frequency to make your amplitude larger, and then you can reach the phase two.
okay, I think that's all.
Thank you.
Okay, so opponent, you can summarize the discussion.
Okay, in the discussion, me and the reporter discussed about the theory of the lasso and how they do the experiment. They say they use the 6-dimensional to analyze the movement of the lasso, and they use 5 experiments to detect when the lasso is moving and colliding, and how do the energy lost to affect the lasso movement. Thank you.
So reviewer, yeah, now you can ask the question.
Okay, I want to ask for the reporter. Do you think, I remember you have the do you think the angle is more enough to consider it to a semi-harmonic motion?
What do you mean by angle? This is the
The angle between the vertical
I never talk about the SHM in that. I am talking about the pivot, and the pivot oscillation is only on the direction of y-axis. So I don't know what do you mean by angle.
Oh, okay. And also I want to ask for reporter and the natural frequencies, and you let the ball to down and hit the knuckle, and the whole process is the string always straight.
You mean slack?
The string, the pivot and the balls between and the string always straight.
Yes.
Always straight.
As far as I observe.
And also, I want to ask, do you think the whole process, do you think have any factor to cause the energy loss?
Yes. Damping.
Also, have only damping to cause the energy loss.
So damping consists of many factors that cause energy loss. So like air resistance, slack, or like collision. So to consider them as the damping is very practical to evaluate.
And what do you think about this? Do you agree that damping is cause the whole energy loss?
I think, yeah, damping cause the energy loss because when the ball collide, the energy will not be fully transferred to another ball.
And also I want to ask your Lego machines will move frequently. Is it right?
Yes, and I have a face portrait and on my appendix here. This is a face portrait of my pivot oscillation.
Do you calculate the
Okay, so time's up. Preparation time for reviewer, 2 minutes. The viewer can text the flow.
And my name is Huang Chao, and I'm from Zhanghua National Senior High School, and my team is Crusader, and today I will review the topic of the lato. And this is a problem statement, and attach a ball to each end of a string and connect the center of the string to a pivot. When the pivot oscillates along the vertical directions, the balls start to collide and oscillate with increasing amplitude. Investigate the problem. And we will focus on the oscillations and amplitude and collide. And the reporter is an overview for the reporter. And the phenomenon is a pivot oscillation along the vertical direction. The balls start to collide in oscillation with increasing amplitude, and there are 5 experiments. And the first is the equivalence of a gravitational field and the natural frequency and resonance and the chaos. And the theory both are the damping and the simple harmonic motions. And the reporter has a good setup, and he told very clearly and showed computer theory and experiments will design and good time management. But I think the mathematical is very complex, and maybe I suggest that he can explain this be more clearly. And this is for opponents, and it's being clear to problems of reporter and clear demonstration of the problem itself and adequate discussion on each problem. And I also suggest that he could have focus on the chart and could deeply to discuss not just the surface, and he can be known more to the problem. And this is a discussions, and the opponent asked the reporter to how to make the pivot move, and the reporter said he used the Lego machines, and I think it is a good way to let the pivot to move in the vertical directions. And also opponent asked why the W is discrete in the page 18, and the report said the lato is a damping oscillation, and we agree that it is a damping oscillation, so it will let the omega to decrease. And also I have asked what have any factors cause the energy loss, and the reporter asked the damping, and I also asked the opponent did he agree this answer, and he also say he agree with it. And I asked the reporter the string always drives to a natural frequency, because I think it is important, because I think if the string not always drives will affect the natural frequencies. And the reporter said yes, he thinks the string is always stretched. Thank you. That's all my review.
Okay, so the reporter can give the concluding remark.
Okay, here is my rebuttal. Okay, so indeed we all know the motion of the pivot is pivotal in this phenomenon, so we use the Lego equivalence to control the pivot. And in the discussion, we talked about the resonance, and my opponent laid immense stress on the phase 1 and phase 2, and which can be described by the resonance. And also the damping is a very critical approach to describe the energy loss, and with it we don't have to discuss about like air resistance or other factors that are difficult to evaluate. And last, I talk about the chaos. I introduced the Lyapunov exponent to verify that the lato-lato is a chaotic motion. And for the reviewer summary, I would like to clarify something. Is I said that lato-lato had, if I didn't give any extra energy, it will damp. But it doesn't mean that it is like some damping system. No, it is not, because we have to oscillate the pivot. So this is a summary of our discussion. So I explain my theory, include like equivalence of gravitational field and also the Lyapunov exponent, and also we discussed about the value of experiment 1. And my opponent asked me about why isn't all the points dense around the magnitude of G, and this is because damping or maybe collision that I discussed in another experiment. So I also clarified the meaning of damping, and I think this is a very good discussion, and I want to thank my opponent and reviewer. So thank you.
Okay, so it's time for questions from the jury. So maybe I would like to ask the reporter first, what does mean the chaos in physical meaning in your experiment?
The chaos is for a very small initial condition variation will cause a very huge variation in the after the time go further.
I mean the physical meaning.
Physical meaning.
Yeah.
Can you rephrase it?
Yeah, just the you use the chaos. Yeah, this term, right?
Yes.
So the any physical meaning, yeah, inside your experiment.
Yes, it means that it is not always predictable, and I use it to explain the steady state of amplitude, and it accounts very well.
Okay, thank you. So any question from jury?
So actually, I have several questions. Look, just especially for the reporter. It looks like you are knowledgeable about nonlinear physics. So actually, to start with the chaotic motion. Oh no, let me clarify. Can you show your equation motion? Let me clarify something.
Equation first. Okay. Now, equation of motion is here.
Yeah, so the other two teams that you don't know much about ODE, right? That's fine. Yeah, so what's omega 0 here? Omega naught here.
Omega 0 means the natural frequency.
So did you roll this equation, write your equation by yourself?
Actually, my teammate also helps me. He is good at math.
Okay. So now let's switch to a chaotic mode. So you mentioned the Lyapunov exponent.
Yes.
Yeah. So but you did not explain, or at least not clear to me, is why when you show the result of the Lyapunov exponent, but you didn't explain why that would correspond to chaotic motion. Can you explain that?
By the definition of the Lyapunov exponent, it helps us to evaluate the difference between
No,
two.
so every experiment you can define the Lyapunov exponent.
Yes.
You can plot that.
Yes.
But why this corresponds to the chaotic motion?
Because it helped me to evaluate the difference between 2 points that their initial condition is very close to each other, and which corresponds to the definition of chaos.
Can you use this graph to explain that?
Yes.
You were talking about the essential definition of why we look at the chaotic motion, but you explain that with this graph.
We can observe a positive slope. A positive slope indicates chaos with Lyapunov exponent. The maximum slope is positive. So, and we can see there is no decay.
What do you mean by slope here?
The slope of tangency.
Any question?
I'm wondering that if you say it's a chaotic system and you mention for example, the sigma as a variable, and you find that it becomes non-periodic.
Sorry, can you repeat it?
I mean, if you measure the trajectory of the oscillator, and delta variable, and you can still find some period, right? But for chaotic motion, it will become non-periodic.
So you mean because I found
Do you measure this data?
yes. So do you mean by that because I have some periodic results, so it doesn't indicate chaos? Is that your questions?
Yes.
Oh, so let me explain. So do you mean the periodic like this or the beat?
The big is like you do the Fourier transform, right?
Oh, Fourier transform here. Yes.
And the Fourier transform is the data is the trajectory.
This Fourier transform is for the beat, in the previous page. Here, the Fourier transform of the beats.
Bits mean
The beats mean like the amplitude of the wave increase and decrease, and yes, it may seem periodic. That's called beat, and the beat is caused by two peaks that are very close to each other.
Following this question, two frequency, which two?
Oh, so let me show the previous Fourier transform since it better shows the beats. So these two.
Yeah, I know these two frequency, but what's the source? What's the source for these two peaks? I mean, the frequency of the two bolts or the oscillator?
Oh, the frequency of the angular velocity versus time graph of the pulse.
Okay, so due to time limit, later, yeah, it will like to comment, yeah, after a scoring. Okay, scoring time.
Thank you.
Okay, so for reporter, 9, 7, 6, 6, 8. For opponent, 4, 5, 7, 5, 4. For reviewer, 5, 5, 6, 5, 6. Okay, so does any comment from the jury? Yeah, we'd like to give any suggestion, comment to all the participants. Okay.
Can we read? I don't know the rule.
Yeah, usually, yeah, finally, yeah, maybe you can give some comment to the student. Now it is almost end. Yeah. If we-
Just one short quick
Yeah.
comment. So I think you guys are really smart and know a lot of and English are very good. But I just in terms of presentation, I think it's better that you explain the physics in a simple term. Not just 12 minutes. So don't try to skip all the details and give us the important physics. Yeah, so that when I go on, I would say, oh, I understand what you're saying, and I remember all the results, not the numerical results or any kind of Latin symbols, right? Okay, just a suggestion.
Okay, so with last suggestion, I would like to close this section. So thank you for your attention and the participants. Okay.